Hello, my name is Josiah Wong, and this is my project for CS231N, and it's called Leveraging Proprioceptive Measurements and Temporal Dependencies to Refine RGB Camera-Based Pose Estimators. I know it's quite a mouthful, but if you just bear with me, it's a lot more simpler than it sounds. And so first we just begin by giving a brief overview and motivation for this project. And so we consider the multi-agent domain, which is often characterized by a high-dimensional state space. And the problem with this is that it's often intractable or difficult to fully observe this entire state space. So we're often in this PUM MGP setting. And so as a result, it's crucial that each robot or each agent within such an environment is able to communicate effectively and or infer accurately these unknown states within the environment. And so we consider this problem statement where we seek to estimate the unknown state space, and we consider that state space as poses of each agent by leveraging temporal dependencies between our observations over time. And those observations consist of a monocular RGB camera images as well as proprioceptive measurements from the given robot's perspective. And so here's our proposed model design, and you can see that we incorporate both of these features, the proprioceptive measurements here as input, as well as the recursive nature of this model, which is captured by the LSTM module. And the other important thing to note is that when we're extracting features from an image, we consider concatenation of both the high-level features from the main output head, as well as the low-level features, which can often capture more the spatial nature of the raw image. And so we extract an early layer from ResNet, and then we compress it via one-by-one convolution, and then we append it to our overall feature head. And so here's the loss that we use for our model. It's pretty straightforward. We essentially regress directly to the quantitative metric that we're looking at. So we're looking at a combination of the position loss as well as orientation loss. And so the position loss is just a simple equally weighted combination of the L1, L2, and L infinity norms. And then for orientation loss, we consider a simplified version of the quaternion distance. And then we also include an additive penalty to encourage restriction of the orientation output to the half sphere. And so this is for stability reasons, as one of the prior works have explored, in order to encourage the estimates to be the same, since normally quaternions are over-parameterized. And lastly, our final loss is just simply a weighted combination of the two. So our data set is we grab new episodes to run simulations on, training episodes essentially in an online fashion. And we run it in RoboSuite. So this is essentially a simulation environment using Muji code that's used for reinforcement learning. And we run each model for roughly 5,000 epochs, which ends up being 25,000 20-step unique training episodes. We consider multiple tasks, so we consider object-based pose estimators, which is this cube and this hammer targets, and you can see them here and here. And then the dynamic target, which is our main goal, which is the robot one effector, which you can see here as an example. We consider two baselines. One of them is removing the temporal dependency within our model, so we replace the LSTM with an extended version of the fully connected output head. And then we also consider removing the proprioceptive measurements, and so we consider the case where we only have visual inputs. And you can see here, this is just an example of what an episode would look like over time in terms of visual observations. We start low, and then the active arm moves up, and so now the perspective has changed. And so here are the outputs, so I'll just loop these really quick for you so that you can see it as the top of the slide. And so you can see visually that our estimator works decently well, surprisingly. And you can see the ball that moves, that's just a visualization of what our model output is doing. And you can see that it quickly converges as soon as it observes within the visual output where the object is, and it converges quickly and stably to that position. Interestingly, the dynamic, because the other robots' trajectories are actually generated in a random fashion as well. And yet it's still able to predict relatively accurately where the pose is for this end effector. And you can see here the quantitative results. And so you can see that our ablative baselines perform worse than our full model. So we show that including both temporal dependencies as well as proprioceptive measurements actually increase the overall precision and accuracy of our model fairly well. And you can see here across the different tasks, our model performs decently well and roughly at the same level of performance. Lastly, we observe the visualization of our model. And so here we take the early batch norm one layer output from ResNet, and we just show you briefly, even though it's really small, you can sort of see how how the different feature activation maps sort of vary between each of the different tasks. And then we show the resulting auxiliary net output, which is essentially the compression of all of these channels into a single channel via the one-by-one convolution layer. And so you can see how for these static cases, for the static objects, which is the cube and the hammer targets, the activation map is very stark. It's almost binary. It's very clear where the center of mass is and where the pose lies spatially within each observation. In contrast, for the dynamic objects, which is the robot 1 and effector target, the feature maps are less apparent, less stark in nature. And interestingly, it actually changes in magnitude over time. And so you can see the activation map actually changes in terms of its intensity and deviation between the highs and the lows. And so this sort of implies how it's necessary to specifically model temporal dependencies within our model, because even though these same features correspond to the same colors, to the same spatial features, the resulting model's outputs are actually changing over time. And so it's important to be able to capture this dependency between these changing activation maps. And that's about it. Thanks for watching.